Welcome to this session, which is a continuation of the application of the reciprocity theorem in the computation of the nth forward going and nth backward going wave amplitudes radiated by electric and magnetic current sources located inside a rectangular waveguide. In the previous lecture, we had considered the computation of the nth forward moving amplitude using the reciprocity theorem radiated by a current source or radiated by an electric current source J inside the waveguide. In this part of the lecture, we are going to write down the expressions of the nth backward moving amplitude of the fields radiated by the electric current source inside a waveguide, as well as the nth forward and backward going amplitudes of fields radiated by a magnetic current source inside a waveguide. So, we saw previously that in order to find out the amplitude of the nth forward moving wave inside a rectangular waveguide, we invoke the test mode, the second set of fields, which involves the nth reverse going wave. In order to do the reverse thing, which is to find the amplitude of the nth reverse going wave, we consider the test mode to be the nth forward going wave. So, we will now consider, in order to find out the amplitude of the nth reverse going wave, the electric field E 2 to be E n plus, which is the forward moving nth harmonic, and H 2 to be H n plus, which is the forward moving nth harmonic for the magnetic field. So, this is the forward moving nth harmonic for the electric field, this is the forward moving nth harmonic for the magnetic field. The set of fields E 1 H 1 corresponding to the scattered modes or scattered fields or the total scattered field inside the waveguide, consisting of the summation over all the eigenmodes, they stay the same as previously. So, now if we do the same exercise once over again, we will find the amplitude of the nth moving backward wave as minus 1 by P n, the volume integral E n plus dot j dV, and that will be the same as 1 by P n. We expand E n plus, and that is E n plus u z E z n dot j e to the power minus j beta n z dV. Let us call this equation 46. So, this is the amplitude of the nth reverse going wave radiated by the electric current source J. So, we have the electric current source J. Okay. In order to find out the nth negative going, in order to find out the nth positive going wave, in order to find out the nth positive going wave radiated by the magnetic current source J, we set J 1 equal to J 2 equal to 0 and excitation with only a magnetic current source M, and there we will find, please do this on your own, in exactly the steps we have outlined for the electric current source. So, there we will find A n plus is 1 by P n volume integral H n minus dot m dV, that is 1 by P n volume integral minus H n plus U z H z n dot m e to the power j beta n z dV. So, we call this equation 47. So, this is the nth forward moving wave radiated by the magnetic current source M placed inside the waveguide. So, we have the magnetic current source M sitting here, and then considering the other problem, which is the nth reverse going wave radiated by the magnetic current source M inside the waveguide, that can be obtained similar So, considering the other problem, which is the nth negative going wave amplitude radiated by the magnetic current source M. So, that can be found as A n minus equal to A n minus equal to 1 by P n volume integral H n plus dot m dV, and then expanding H n plus, it will be 1 by P n volume integral H n plus U z H z n dot m e to the power minus j beta n z dV. So, we call this equation 48. So, P n in all this is given by 45. Okay. So, this completes the expression or rather the expressions for the forward going wave amplitude radiated by the magnetic current source and the reverse going wave amplitudes radiated by the magnetic current source placed inside the waveguide. So, they can be exactly derived, as I said, following the similar steps for the electric current source. This concludes the section on the application of the reciprocity theorem to compute the forward and the backward moving waves inside the waveguide. Thank you.